Well, welcome once again to Bruce's Colorado Rocky Mountain Shop. And today we're going to take a look at an IEC F34 function generator. This function generator came out in the early 70s and became, I think, a rather famous lab piece of equipment. Showed up on a heck of a lot of benches across the country because it provided features that you couldn't find otherwise, and it combined them all into one unit. Um, I believe these things ran around, I don't know, $1,800 at the time they came out, 71, which had to be at least twice that in today's money. But well, I've opened up the F34 and serviced all of the pots and switches, cleaning them. I also cleaned the board off with some contact cleaner. And just figured since I had it open, I'd give you a look at what the inside of this baby is. This was designed and built in the early 70s. There are integrated circuits in here. There's several of them over here, a couple of them here. But the rest of it is populated with transistors. So it's a hybrid. And the engineering and workmanship that went into this was really quite nice, quite impressive. Same thing, the bottom side is, there's less down here. We just see the bottom of the board mostly, and a couple of range switches, power supply. But I thought I'd give you a look. Even if this was, if this thing had been totally dead and I was going to throw it away, I would not throw it away. I would remove the parts, maybe get rid of them. But this chassis alone, this is cast metal. It's got to be 1/8 of an inch thick. It's an impressive cabinet. Could be used for a lot of things. But it's working beautifully, so let's move on. We'll take a look at it. The F34 it'll produce sine wave like we're looking at right now. It'll produce triangle waves, square waves. I'm hoping that we can see that clearly. It'll put out DC that you can vary. You've got pulses. You can change the pulse width on. You've got a ramp. We'll speed it up a little more. There we go. So there's a ramp. That ramp's value can be changed quite a bit. I think we can hit 7-8 volts with it. But in order to do that, I have to increase the display. And we'll bring this up. Let's go ahead and put her back on. And then we'll increase the amplitude. All right, right there is 7 volts from start to end of the ramp. And there's actually more available. I mean, we can change the vertical on that, and let's see what we can get here. All right, so 1, 2, 3, 4, 5 times 2 is 10 volts. So we've got a 10 volt ramp we're taking a look at right now. It's kind of nice to have a ramp feature for your bench if you need to drive something with a timing ramp. Kind of hard to come up with otherwise. The function generator will generate these frequencies, these outputs, over a range from 0 to about 3 megahertz. And we can produce them continuously. Let's go back to a sine wave here. And we'll put ourselves back on the screen. Drop the frequency down a little bit, as we will also the gain. Yeah, like that. All right, so right now we're working at approximately 5,000 hertz. We're 0.1 milliseconds, so per division, and we're getting about one cycle every 2 divisions. So that would be a 0.2 second period. And that would be about 5,000 hertz. It has a calibrated dial, so we can dial in the frequency that we wish. 1.5. This would be 20K right now because we're 10K on the function switch, 2 on the dial, so that'd be 20K. Let's see. We are right now, that's 2.5. 1, 2.5. 1, 2.5 divisions. And we're 20 microseconds, so that would be 50 microseconds period. And so 1 over 50 microseconds, we are talking 20,000 hertz. Okay, so right now I am 1, 2, 3, 4 up and 4 down at 1 volt. That's 8 volts peak to peak with a 3,000 hertz signal. 3 on the dial times 1K on the range. Now let's take our range all the way up to the maximum of 1 meg, and that gives us 3 meg. And we notice that as I move this thing, we dropped. You'll see the bottom come up and you'll see the top come down. Okay? We didn't drop a lot, but let's see. We were at 4. We are now at 3.6. 3.6 divisions vertically. We're going to do some math in a minute here, and we're going to figure out what the bandwidth is on this. The 3 dB point would be at 2.8, which we haven't reached 2.8. We're still above that, so we were then 3 dB, but we're going to calculate how many dB we are that we've dropped, that we are not flat, or from 0 to 3 meg. Okay, here's our formula for calculating the dB loss. 20 times the log to the base 10 of V1 over V2 equals dB. V1 would be the voltage that you dropped to. V2 would be the voltage that you started with. So if V1 is 3.6 and V2 is 4, V1 over V2 is 0.9. Log to the base 10 of V1 over V2 is negative 0.04. And then the full dB loss would be 20 times that, which is a negative 0.915. So what we just did a minute ago showed that we were under 1 dB of loss from 0 to 3 megahertz. If you had 3 dB of loss, we should have came down to 2.83 volts. That's what this calculation shows here. All right, so We are flat within a dB from 0 all the way up to 3 megahertz, which is the limit of the unit. And that's impressive. Let's take a look at well, we've already seen the functions. There's our square wave. There's our triangle wave, sine wave, and the pulse, which we can vary. So for various testing and so on. Let's take a look at a continuous sweep. And we go back to sine, and I will what I do now is I set my dial for the minimum that I want the sweep, where I want the sweep to start at. So the minimum value of the sweep, which I'm going to go all the way down to the lowest end, whatever that is. And then we will take the black dial that's back here. It has a little tang on it. And we're going to move that black dial all the way around to where it hits a stop over here. There, we hit the stop. And then we're going to reduce our sensitivity here a little bit so we get to see the screen a little clearer. And now we're going to slow the speed of the scan down so we can see what's going on. And we're going to increase let's decrease. Yeah, that's better. Now if I slow down my scan, you can see a little more easily what's actually happening here. So when we start the scan, we're at a low frequency. Therefore, our period for the waveform is large. So those are low frequencies. And then as time goes on, the frequency gains and goes faster and faster and faster. And then you actually see it kind of become very small on the right side, and then it restarts again. If we wanted to take a better look at the high end, then I just drop my frequency even, my time-based frequency even more, and we can see what's actually happening here. Now that's to 10K. If I go to 100K, same thing. It's just going through a much larger range of frequencies. So it starts out slow. You can kind of see the spring in the beginning, but then it goes very fast because it's got to cover, 10 times more frequency range than it did. And then if I go to the 1 meg range, you just real quickly see the break for the low frequency, and then it becomes a blur as it zooms off into the high end. I can up my sweep rate, and we can start to take a look at the high end, and we can see that yes, we're still sweeping. So what do we do with that? Why do you want to have sweep? Well, if you want to be able to find out how things react to different frequencies, then a sweeper is a very handy thing to have, because you can put a swept signal over a device that reacts to frequencies, and you can study what happens as the frequency changes on that device. You can take a look at it. And so like if you were building a filter and you wanted to filter out, something, maybe a kilohertz. You wanted to filter out 1 kilohertz, and you wanted to make sure that you had a band pass of some very tight amount where only 1 kilohertz came out, and anything 100 hertz either side of that, didn't. Well, you need to be able to produce something that's going to run through all of the frequencies of interest, and then you can see the result coming out of your filter, and it'll show you what's happening. I got a little demonstration that we can run. I've done this before. We'll do it again. So give me a minute. We'll set it up. Okay. We've hooked up a little device. It's called a ceramic resonator. This particular resonator is made to resonate at 455 kilohertz. That's an IF frequency used in a lot of AM radios, or at least used to be. And we are taking the output of the sweep generator and we're running it in through the ceramic resonator. And then the other side of the ceramic resonator we have the probe tip for the oscilloscope. So that runs into the oscilloscope, and we're running on channel 1. And I've adjusted the frequency up here for my scan so that I am very close to 455. I start at about 400 and I end at about, 550, something like that. And then I'm taking a look at what happened on the scope face. Now, if I was to vary my sweep bend, you can see that the trace on the screen changes. I'm sweeping a lot further out. And then right about there is 455. And then here we actually see a couple of traces. We're going to take a look at that. All right. So what we see is that the trace starts, and we get a little bit of a voltage spike as it starts. So when the frequency is real low, we got some voltage. But then as the frequency starts to sweep into the range of the 455, we see that the voltage is small in this region. And then all of a sudden we get this spike. And then it drops down quickly, gets small, even smaller, and then fades very quickly as the frequency goes up. So I'm taking a look at the transfer function of this resonator. I am resonating about the 455 kilohertz point. Okay, like I say here, we're peaking at 5, 10, almost 15 volts out of that resonator at 455 kilohertz, and otherwise we are down around maybe a volt or two. So the resonator is definitely resonating and performing its function at 455 kilohertz. Now we could take a look at something else. Let's take a look at a filter network. Okay, so what we have here is actually a plug filter. You would plug your plug into the back of your instrument here, and the other end would go into your socket. And built inside of this socket is a little set of coils and capacitors that act as an RF filter, and it filters any radio frequencies that might be trying to come in. It tries to prevent them and only passes the low frequency 60 hertz signal that you have to your scope. So we've got this wired up to the scope, and we're bringing in our frequency. We're sweeping over the 3 megahertz range, and we're going to take a look at the results on the scope. So as we can see, we start out at a high voltage, roughly 4.5 volts, and then as the frequency increases until it gets to the end of its scan, we're constantly dropping, and at the end we're, well, I don't know, something in the vicinity of about a half a volt, maybe 1 volt peak to peak. So it is acting as a filter for RF. As I increase my frequency, then I'm going to see that it's even more dramatic. We get a greater spike in the very beginning, and as compared to the rest of the frequency band. So there's an example of what you would do with a sweep generator. You would also check frequency response of amplifiers. If I want to know that my amplifier delivers true fidelity from 20 to 20,000 hertz. Then I want this thing to scan from 20, and I would set the end scan for 20,000. So here would be roughly 20 to 20,000 right here. And then I would test my amplifier. We're right now still going through the plug. I would test my amplifier and see how I fall off as the frequency goes up. And if I first started out with 4 divisions up, and I see myself fall to 2.83 divisions at the end of the trace, that's my 3 dB point. And those are important specs when you're speccing out an amplifier. Another example of what you would use that for. You've got capability to do the continuous sweep. You've got a triggered sweep where you can either manually trigger it with a button here. See if I can do it. Yeah, you can see it quickly triggered. Or you can put in a synchronized trigger signal on an input here. And you have what they call a frequency analog output. You get a voltage from 0 to 5 volts coming out of this terminal that you can measure with a VTVM or a DVM or whatever. And as your frequency goes up, you'd see the voltage go up with it. So you check your calibration at 0, check your calibration at the maximum. It should be between 0 and 5 volts. And anything in between, you just linearly be able to read it out on your DVM, and you could calculate what frequency you were at. Be just as easy to monitor the output and use a frequency meter, but they weren't quite as common back then. But you could read the frequency coming out directly. The other thing this thing does is it has a voltage-controlled generator input here. And you can put a 0 to 10 volt signal in on this particular port, and it'll change the frequency coming out of the unit proportional to the voltage, which is interesting. Let's all right. Let's go ahead and demonstrate. All right. So now I'm feeding a DC voltage in from a power supply over here. I've got 9.8 volts dialed in from that power supply, and I'm feeding it in. And right now I've got the dial set to the minimum, so I should be producing a very, very low frequency. But I'm putting the voltage in on this voltage-controlled generator, and I'm producing a signal that is. Well, let's take a look at it. Right now we are 2 divisions per cycle, and we are running 20 microseconds per division. So that's 40 microseconds that we have for a period. That'd be about 7,142. Cycles per second, right? Okay, right now on the screen I'm having I'm going to call that a minimum trace right there. That minimum trace is about 66.5 hertz. And that's with the dial set to minimum. Now I've got a voltage coming in, or coming from a power supply over here. Right now I don't have anything dialed in. But I'm going to start dialing that voltage up. And we should see that frequency goes up dramatically. So at about 11 volts input, we're getting 30 kilohertz, 30.24, which would be about full scale on this 10 kilohertz position of the range. 3 times 10 would be 30 kilohertz that we could get on that. And if I turn my time base up here, we can see the 30 kilohertz signal. And we could calculate too by taking a look. We've got 1, 2, 3.2, 3.3 centimeters, or divisions I should say. 3.3 divisions times 10 microseconds per division. 3.3 times 10 would be 33, 1 over 33 times a million. And we would have 30,300 cycles. So my voltage, I'm going to drop the voltage now, and you're going to see that the frequency goes down. We could change our range to help follow it. It's supposed to be 1,000 to 1. Okay, another little feature of the unit. We can have a signal being generated, and then we can offset that signal with a DC voltage, so we can raise it above maybe a digital threshold or something. So let's take a look at that. Right now we're in the DC function on our oscilloscope, so I'm able to read DC on here, but right now the only thing I have is an AC signal. But if I pull the offset button here on, right now it's at 0, but if I start to rotate it clockwise, you're going to see that I am raising my waveform above 0. I've got to resync it. There we go. So I am now 1 volt above, actually 2 volts. My 0 point on the AC signal is 2 volts above where it was earlier. 1, 2. So I have a 2 volt offset, and I can take her down the other way if I wanted. Could have a -2. That's actually a -3. -2. Back to 0. Can resync it. There we go. So, boy, this thing is just loaded. We've got a sync output that provides 2 volts peak to peak. We have an output limit light. If I try to overdrive my output to where I would go into distortion, then that light should come on. Alright, so my output limit light is coming on to show me that I'm trying to do too much, put too much output out there. So if I reduce it, the light goes off. We're good. Pretty much that's the Whirlwind Tour. It's a beautiful device, very sophisticated at the time that it came out. Still sophisticated, just different era, different electronics, but the thing is still working. It works beautifully. It does things that other units don't do. Worthwhile bench piece, and it's in good looking shape. Very few nicks or scratches. We are missing the handle up here. Didn't come with the unit, so whoever had it on a bench and removed the handle because they had something sitting on top of it, I'm guessing. It does have a stand, has a wire stand that pulls out down below. Very clean panel front. A couple of the knobs have a crack or so in them, but they work, and they'll hold up for years, I think. Very worthwhile unit. So thank you for listening. Happy bidding, and we'll see you again.